Okay, good morning, everyone. So you should have all got your midterms back, and I am not going to put out a solution for the midterms. Instead, um, I'm going to have you do the problem that gave everyone the most trouble for homework, and so eventually you'll get a solution for it. And that was problem 2. So we're going to talk, I'm going to give you some hints about problem 2 in preparation for you doing it on the homework. And it's partly because I'm determined that everyone in this class will be able to do problem 2 and problems like it. The reason is because it's an extremely useful and very common trick. Maybe I shouldn't call it a trick. Maybe that's not a good word. I should maybe call it a method because it's more than just a trick. So very common method. It's so common that we've actually seen it several times before. So first of all, we're in this problem, we're dealing with a perturbation Hamiltonian, which is some constant times the dot product of two angular momentum. Okay, and so we have seen this used in, not in chronological order, but in sort of order of importance in the fine structure of the hydrogen atom, where it showed up as the spin orbit term. Can't spell this morning. Okay, which we called HLS, and it was proportional to just exactly L dot S. Okay, and we also saw it in the hydrogen atom ground state hyperfine. That's the 21 centimeter line, where it showed up in a slightly different disguise as the dot product of the electron spin and the proton spin. And then it showed up in the hyperfine of excited states of the hydrogen atom. Okay, and there we had to do a little bit of preliminary work to discover that that term was proportional to the dot product of the proton spin and the total angular momentum of the electron, including both the spin and the orbital. And that was after using Landé's formula. So there was actually sort of a good amount of preliminary work before we put it in that form, but we did have that. And we actually did the ground state of the hyperfine last semester as well. And this week, we are going to be using it yet again for multi-electron atoms, where again it shows up as the dot product of orbital and spin angular momenta. So that's this week. Okay, and as if that weren't motivation enough, you will also see it on another homework problem this week, which I haven't put out yet. So this will be homework problem 2 on set 6. And you will see it many other places. It's the generic thing to try if you see the dot product of two angular momenta. Okay, so what's the method? Let me remind you what it is. So you have a total angular momenta, which is the sum of the two, in this case, orbital plus spin. And so that means if you just take that operator and dot product it with itself, on the left-hand side, you get j squared. That's the dot product of j with j. And on the right-hand side, you get L squared plus S squared plus the cross term, which is 2L dot S. Okay, and so that means you can solve for L dot S. L dot S is 1/2 j squared minus L squared minus S squared. Now, the thing that is going to make this work is the operators J squared, L squared, and S squared have very nice commutation properties. In particular, they all commute with each other. And so when you see that, you should be thinking, aha, complete set of commuting observables could include them. And in particular, they also commute with the radial coordinate. That's just related to the fact that if I do a rotation, remember angular momenta are the generators of rotation. So if I do a rotation, I'm just rotating my radial coordinate and the length of it doesn't change. So they commute with the radial coordinate r. And because they commute with the radial coordinate r, they commute with any function of r. So they commute with what's told you in the problem is the arbitrary spherically symmetric potential V of r. And they commute with the kinetic term. Again, this is just the fact that the kinetic term is rotationally invariant. And not only that, they also commute with the z component of the total angular momentum J. So all of that put together means that a complete set of commuting observables is the Hamiltonian, because everything that I've included previously is what the Hamiltonian will depend on. They all of these things commute. L squared, S squared, J squared, and then I can throw in J sub z. Notice I can't throw in L sub z because L sub z will not commute then I won't have a complete set of commuting observables. And so this is a complete set of commuting observables, and therefore an orthobasis, a natural orthobasis associated with this will be my radial quantum number corresponding to the Hamiltonian, L, S, J, and M sub J.
Professor?
Yes.
Could you explain one more time, how did the radial coordinate come in?
So the radial coordinate comes in because there's a part of the Hamiltonian that depends on your spherically symmetric potential.
And it commutes with those, aren't those energies?
Aren't what energies?
Like the J squared and the L squared and S squared, wasn't that like orbital angular moment? Oh, you're saying since those commute with the Hamiltonian, that's what I'm saying. The
They all
R,
commute with each other and they all commute with the Hamiltonian.
but does R, wasn't R distance?
Yes.
How does distance and energy commute?
So the distance and the energy don't commute. We're not saying they do.
I thought you said it commutes with the radial coordinator R up there.
Yes, these things all commute with R. Therefore, they all commute with V of R. And they commute with P squared over 2M. And so our Hamiltonian is something like this. Okay, that's the unperturbed Hamiltonian. And so all the pieces of it commute with J squared, L squared, and S squared. So that's why this and this and this and this and this as well all commute with each other.
See, what I'm not understanding is if R doesn't commute with the Hamiltonian.
Right. That's why we're not including R within our complete set of commuting observables. It doesn't commute with the Hamiltonian.
So what I'm not understanding is if that J squared, L squared, S squared commutes with the Hamiltonian, they commute with R. How is it that R doesn't commute with the Hamiltonian? I'm a little bit confused here.
So R doesn't commute with Hamiltonian because it doesn't commute with P. It doesn't commute with P squared over 2M.
Oh, but it commutes with the rest of those, right?
Yes.
Okay, thank you.
That's why we can't add R to the complete set of commuting observables.
Thank you.
Okay. All right, so we've got an orthobasis, and this is known as, this is just terminology, this is the total angular momentum basis. Okay, now the good thing about this basis is that acting on the states in the basis, J squared, L squared, and S squared are just numbers because that set of states are eigenstates of J squared, L squared, and S squared. That's how we construct them. And so specifically, J squared is H bar squared J times J plus 1. L squared is H bar squared L times L plus 1. S squared is H bar squared S times S plus 1. And in the problem, you're told that S in this case is 3/2. So you know exactly what that number is. Okay, and so since all of those are just numbers acting on the state, so is L dot S, and therefore so is our perturbation Hamiltonian. Okay, so is L dot S, and so is this thing. And more generally, anytime L dot S is an important operator for you, it's a good idea to choose the total angular momentum basis defined by this, because in that basis, L dot S is just a number. It's a number that you can compute just by plugging in these things. Okay, so in parentheses, I will write here. Many of you wrote on your midterms, oh, if I just had written down this matrix on my formula sheet, it would have been much nicer. But actually, you don't need any matrices. To do this problem. You didn't actually forget to write them down because you didn't use them. And not only that, you don't want to use the other basis, which would be, well, corresponding to this complete set of commuting observables. Okay, and that would, so that corresponds to what's called the product angular momentum basis, which is denoted N, L, S, M sub L, M sub S. Okay, and why would, then what use is that basis? That basis is useful when you have something like the following. Suppose my Hamiltonian, my perturbation Hamiltonian was something like a constant magnetic field dotted into L, or a constant magnetic field dotted into S. Then I choose my constant magnetic field to be in the Z direction. Okay, and then the operator that turns into a number, or the operators that turn into numbers acting on the product basis, are the Z components of L and S, because they are the eigenstates. And so the product basis is not useless, it's just useful for a different kind of problem. It's useful when you have a special direction, which you then call the Z hat direction. Okay, so that's a parenthetical aside. And then there are problems where both of them are important. For example, I might have an external magnetic field that has these kind of operators in them. And I have this kind of perturbation. So certainly that occurs, for example, if I put the hydrogen atom, including the fine structure, in a magnetic field. We also had a homework problem about that. And then you have to do a judgment as to which one is the larger and more important term. And if they're both comparable, then no matter which basis you use, you're going to have to do some diagonalization. But as long as only one term is the important one, namely this one, If we see that, we should be thinking total angular momentum basis, because in the total angular momentum basis, we use this trick, and then these are just all numbers. Okay, the only other thing that you need to do the problem is you need to know what J's occur, because essentially in the problem I gave you L and S. And the answer to what J's occur comes from addition of angular momentum. Okay, and applied to this situation, if I have L and S, and I combine them, the results in the total angular momentum basis are going to range from L minus S in absolute value up to L plus S. So this is the maximum J you can have, and this is the minimum J you can have. Okay, and the dot, dot, dots means you go in integer steps. That's true for any addition of angular momentum. That's always how you construct the total of two angular momenta, which again, you will be using, we'll be using it several times going forward in the course, including on the next homework set, where I'm going to have you add together the angular momenta for 3 electrons. Okay, so hopefully with those hints in that direction, then you will find this problem to be very straightforward, hopefully. It was intended to take you about 10 minutes and be 3 points, but I guess it didn't work out that way. Okay, so that's a learning thing for us. Any questions on that? Or what the strategy should be for this?
Professor, this last part, I was always confused about these tensor product things. Just the very last line, could you just briefly go over that, please?
Okay, so this is just saying if I have angular momentum L, and I'm combining it with angular momentum S, and I want the total angular momentum, and so that's going to be J, and I want to know what J's occur within that addition of angular momenta. And the answer is I get each and every value of J starting from L minus S and going up to L plus S. And with increasing by one on each step. Okay, so it's just a formula that tells you which J's actually occur when you add 2 angular momenta. Okay?
Thank you.
Sure. All right, so you'll get to do that for homework. And so now let's go back to where we were in the lecture, which was talking about, we were about to start talking about multi-electron atoms. And so one thing I should say right off the bat is we're not going to be actually solving any complicated differential equations or anything. This is not that it can't be done, but that it's indeed very complicated. And so our treatment is going to be more qualitative as we go. So features of this are, first of all, that the Hamiltonian is complicated, so we'll write it down, but we won't actually solve it. Instead, we'll more describe the qualitative features of the solution. So treat qualitatively. And so what we have in mind is if we were going to solve it more precisely, we would be doing either perturbation theory or a variational principle. And so we've already sort of gotten some experience in how that might go because we treated the helium atom, which had 2 electrons, using both of those, using perturbation theory and the variational principle. And we saw that the variational principle did a little bit better. but you could do both. And the key idea behind both of these is to find an appropriate unperturbed Hamiltonian. So you might say, well, in perturbation theory, that's clear that the perturbation Hamiltonian is how we define our unperturbed states. But if you think about it, you're doing something similar for the variational principle. Because for the variational principle, you need some trial wave function to start off with. And how are you going to choose a trial wave function? Probably by finding the solutions to some appropriate unperturbed Hamiltonian that you think might give you something close to the right answer. Okay, so this will either give unperturbed states or trial states as its eigenvalues, as its eigenstates. Okay, and the third ingredient we're going to have to be careful and is going to be extremely important is the fact that electrons are identical particles. And so we will have to use the information we get there. In particular, this is going to make sure that we use the Pauli exclusion principle, which says that two electrons can't be in the same state. And we're going to apply that at the level of the unperturbed states, or equivalently in the variational principle to the trial states. I'm just going to write unperturbed with the understanding that if we're doing the variational principle, unperturbed really means trial. All right, so now let's write down our Hamiltonian for a multi-electron atom. Okay, so multi-electron atom, I'm going to say the nucleus has charge Z times E. So Z is some integer. All right, so what's the Hamiltonian? The Hamiltonian is going to be, first of all, a sum over all the electrons, so from K equals 1 up to Z, of their momentum squared. So I have an index that tells me which electron I'm talking about, but they all have the same mass. Okay, and then there's a potential for each one of them to the nucleus. So I'm going to again sum over all my electrons. And then I have Z E squared over R sub K. Again, K labels which electron I'm talking about. But then the electrons repel each other. And so I have some sum over L not equal to K. L is again an electron label of the charge of the electron squared divided by the distance between them. So RK minus RL. This is where it gets complicated. And then I have to remember there's a factor of 2 in the denominator. And the reason for the factor of 2 is just that when I'm summing over both L and K, that means I'm including every pair of electrons twice. And so to avoid double counting the energy of the interaction between them, I have to divide by 2. Okay, and then there's the spin orbit coupling. And one thing you learned for homework on a homework problem is that when you go to larger Z, the spin orbit interaction tends to grow fast. It goes like Z to the 4th power. And so if we're talking about more and more complicated electrons, this is going to get larger and larger. But nevertheless, we're going to treat that as a perturbation. And then I should mention there's other things.
Sorry, Professor, could you please repeat that last statement? When you go to larger Z, what happens?
When you go to larger Z, the spin orbit becomes relatively more important because it goes like a higher, it behaves like a higher power of Z, namely Z to the 4th, whereas the energy contributions from the rest of this go like Z squared when you work out the eigenvalues.
Thank you.
Okay. And then there's other things here that we're actually not going to talk about at all. There's the relativistic kinematic. It's not that it's not important. In fact, it's of the same order as the spin orbit. It's that it's basically has no particularly interesting properties because it's spherically symmetric and all that stuff. There's the Darwin term. There's the hyperfine, which tends to be smaller, plus ... Okay, so all of this, we're just going to not talk about them, even though if you were doing this professionally, you would want to include them. Okay, and so that's our Hamiltonian, is everything that's not circled there.
Could you please say the name again? You said it's the kinematic. What was the name again?
The relativistic kinematic term. That's the thing that goes like p to the 4th power. And it's divided by the speed of light squared.
What does it do?
It's just a term in the Hamiltonian that takes into account the fact that the electrons are relativistic.
Thank you.
Okay. So we saw that in the fine structure. That was part of the fine structure Hamiltonian for the hydrogen atom. Okay, so this is a complicated enough Hamiltonian, even without these terms on the end that we're not going to include. And so we need some way to deal with them. And one way, actually, it's a variety of different methods that are all part of what I would call the central field approximation. Okay, and the central field approximation basically amounts to dividing this into perturbed and unperturbed parts, or perturbed parts and unperturbed parts in a clever way. And so let me say what we do first. I'm going to rewrite the Hamiltonian like this. Okay, there's my p squared. This is my kinetic term. And then I'm going to add to it a function that I'm going to call u. Okay, and this part I'm going to call h0. I haven't told you what u is yet. And then there's going to be this part. So look what I've done. I've just subtracted off u again. So really, I've done nothing. No matter what u is, I've done nothing really. But now I add in the attraction to the nucleus. And then I add in the really complicated part. Okay, and then I add in my spin orbit coupling. Okay, and so all of this stuff, like there, I'm going to call that W. And then this part, the spin orbit, I'm going to leave separate. And so all of this stuff, I guess this includes the minus sign, technically. And then all of this stuff together, we're going to treat as a perturbation. So I'm treating all of that as a perturbation, but for future reference, I'm also splitting the perturbation into 2 parts, which if you think about it, we also did for the fine structure. We had 3 terms in the perturbation, but we split them into 3, and then we treated them individually. Okay, so I've added and subtracted my u of r, and now we should decide how we should choose it.
I'm sorry, Professor. Is that a z or a 2 in that third term? For the e squared over, is that z rk minus rl, or is that a 2?
This is a 2, just like that's a 2.
Thank you.
Okay, so we're going to choose our potential, u of rk, because it is a potential energy, using semi-classical reasoning. I should say there's actually different ways of choosing U. There's no right way and no wrong way. Okay, but the motivation that we're going to use here is Gauss's law in electrostatics, which tells you the following. Okay, that if you have a spherically symmetric potential, then at a point R, the potential and the electric field there only depend on the charge contained within R. So inside R. Okay, so let's draw a picture. Here's our nucleus with charge Z. And then here's some point where there's an electron sitting. Okay, and we're interested in that distance is R. And then within it, though, there's an electron cloud. Let me draw it with some shading here. So there's some electron cloud here that's spherically symmetric. Pretend this orange blob is a sphere. And so some of the electron cloud is inside and some of it's outside. Okay, and so if you are at this point right here, the only part of it that matters is the part that's closer than you are. Okay, and so for small r, the electron just sees the nucleus because all the rest of the orange cloud is farther away. So sees nucleus only. But for large r, if you're sufficiently far away from the nucleus, then most of the other electrons are closer than you are to the center. And so for large r, the nucleus is screened by the other Z-1 electrons. It's Z-1 because we're not counting the electron that you are when you are deciding what your potential is. Okay, so that motivates the following choice for U of R. I'm writing it as a classical potential, but then you promote it to an operator. Okay, for small r, it should be something like minus Z E squared over R. That's small r, no screening. Okay, and for large r, it should be minus E squared over R. Because there are Z-1 charges screened. So you start with a Z from the proton, and then you have Z-1 with the opposite from the other electron. And so it should be some potential like that. So if we draw a picture of what our potential looks like, our U of R potential.
I'm sorry, Professor. I fell behind. Could you scroll up a little bit? Thank you.
Okay, so this is a graph of U of R versus R. And so we can draw two versions of this. One would be the relatively weak potential from a single charge, something like that. That would be minus E squared over R. And then there would be the relatively stronger potential for the, including the nucleus. So that would be minus Z E squared over R. And so what we're saying is when you choose your U of R, at large R, you should be up here, close to the blue dashed line. And for small r, you should be approaching the red dashed line. So there's a lot of different U of R's you could choose. And so different people choose different things. And the idea is you're supposed to choose it so that it obeys, at small r, it obeys one thing, and at large r, it obeys something else. And what it does in the middle is sort of up to you. And when I say it's up to you, then what is your goal when you're choosing it? So here's your goal. If we go back up here, we're splitting our Hamiltonian into an H0 part and everything else. And so we want to choose U of R so that the unperturbed Hamiltonian is going to be the big effect, and this is going to be a small effect, either as a variational principle or as a perturbation theory. And so you kind of have to play around with U of R in order to make this be valid as a perturbation. That means its effects should be relatively small compared to this. Okay, and so to first approximation, this right here is all we're going to deal with. And then we just are going to imagine treating this as a perturbation later, if we have to be very precise about things. Okay, so let's go back now to the spin orbit part. Okay, so there's a spin orbit Hamiltonian, which is a sum k equals 1 to z. So again, we're just summing over all the electrons. There's some function which depends on the radial coordinate, which I'll tell you what that is in a second. That's the Greek letter squiggle. And then there's the dot product of the orbital and the spin for the electron. And squiggle is minus a sum over all the other electrons of this stuff. E h bar squared over 2 MEC squared, 1 over R times the derivative of the potential, of the electrostatic potential. So I guess I should have, I'm writing this in a classical way. So let me change this big R to a little r. So in the end, we promote it to an operator though. Okay, and then where I need to tell you what the electrostatic potential is. This should have been a K, by the way. So this is the potential seen by the kth electron. And the electrostatic potential seen by the kth electron is minus z e squared over r from the nucleus plus a sum over all k of e squared over r minus rk. Okay, so this is going to be very complicated, and therefore that's going to explain why we're not going to actually evaluate this. Really, all we're going to end up caring about mostly is what is the sign of this. And even that, we're not going to worry about in detail. We're just going to take it empirically. In other words, we're going to say, experimentally, we find that it has one sign or the other. Okay. So that's all of our Hamiltonian. Let's go back up here and look at our H0 again. And so we imagine that given a U of R, which somebody has chosen appropriately, we want to solve this thing, and we want to think about what its properties will be. And so its properties will be very similar to the hydrogen atom, but not exactly the same. And we call the states that you get from that orbitals. So orbital states equals eigenstates of H0. Okay, and if I write a wave function for them, I'm going to write phi for them. They're going to depend on an orbital quantum number n, a angular momentum L, and a S. Okay, and if I write their the wave function for a state like that, it's going to have a radial wave function, which depends only on R and depends on N and L. And to differentiate this from the hydrogen atom case, I'm going to put a superscript U on it. So that means that I've chosen some appropriate potential U that I think basically U is mocking up the effect of all the complicated electron interactions with this electron. Okay, and then I'm solving some perhaps horrible differential equation to get that. But then the angular part of it, because this is supposed to be an angular momentum eigenstate, that's just going to be a spherical harmonic. So at least that we know. And then there's the spin part. Okay, and that's going to be either spin up or spin down for a single electron. So these are single electron states. Okay, so notice that if we go back up to our H0, our H0 here had only a sum over K. It didn't have a double sum like here. The double sum is where all the trouble comes from. So because this is a single sum over a bunch of identical Hamiltonians, we can just solve these one at a time. Okay, and that's what these orbital states are. Okay, so just to make some notes here about this, this R function is not the same as for hydrogen, not even after rescaling for Z. Okay, and that's because our central field potential is not the same thing as minus Z E squared over R, but it's qualitatively similar, at least we hope. And so we can use some of the same terminology to describe these states. So in particular, our principal quantum number is going to be an integer, which is greater than or equal to 1. The orbital angular momentum quantum number is going to be less than or equal to n minus 1. The number of zeros is, by definition, the number of zeros of that function is n minus L minus 1. And larger L for fixed n gives a smaller expectation value of the radial coordinate. Okay, and then last but not least, I should tell you what the unperturbed energy eigenvalues are, or something about them. So these will increase with n. So one way of thinking about that is just that the number of zeros is increasing with n. And if the number of zeros is increasing with n, that means the function has to wiggle more because it has to wiggle up and down, right? So if I were to graph it, right, if I had large n, it might do something like that. And the more wiggles it has, the greater the kinetic energy contribution it has, and that will contribute to the total energy. So it increases with n, but unlike for hydrogen, it also depends on L. And how it depends on L exactly depends on what you chose for your central field potential. But the principle again is that you should choose your central field potential in order that these curly E's are as close as possible to the final E's that you get. So you have to do a little trial by error. You have to choose your central field potential, compute the curly E's, then do perturbation theory or the variational principle to find the total E's. And then if it's wildly different from your curly E's, that means you didn't choose a very good central field potential U, and you need to start over again and do it again, which is pleasant. Okay, so now we have some orbital states. And for orbitals that have the same n and L, there are how many states? So first of all, there's going to be a 2 for spin. And then there's going to be 2L plus 1 of these for minus L less than or equal to M sub L less than or equal to L. So that's just the degeneracy associated with the Z component of the angular momentum. And so the set of all of these states that are at this point degenerate are called a shell. And so if I'm talking about some electrons, I can tell you what the unperturbed state is, which again is supposed to be close to the final perturbed state, hopefully, by telling you how many electrons there are for a given shell. And so for the next few lectures, next couple of lectures, we're going to be talking about how to think about electrons filling up shells. Not just how they fill up the shells, but in what angular momentum states they will arrange themselves when they do so. Okay, so just like for the hydrogen atom, shells are labeled NL, but then you have a code where you replace L by S, P, D, F, etc., according to whether L is 0, 1, 2, 3, etc. And so now if I look at how many electrons there are in a given shell, the number I can put is 2 for S, 6 for P's, 10 for D's, and 14 for F's, etc. So this here is the total states per value of n that you choose. All right, so we will start talking about the electron configuration for multi-electron atoms, which of course is one of the great successes of quantum mechanics, is that we can understand this. First, it was done historically in a very qualitative way. And then as time went on, and especially with the advent of being able to apply computers to the variational principle, we've got a very sophisticated way of understanding the structure of atoms and the energy level of atoms. Okay, so that's a good place to stop. But one thing I wanted to ask you is your collective thoughts on when the homework should be due. So let me ask, because I know some of you are in some classes and I'm not sure what days your homeworks are due in other classes, let me ask this, is Monday or Tuesday a good day or a bad day to have homeworks due? So somebody needs to pipe up and be spokesperson for the group.
I guess I will. I know that E&M is usually due on like Sunday night Mondays. So I think that later in the week might be better.
Later in the week might be better. Okay.
I would prefer middle of the week personally, but
middle of the week. Okay.
I prefer later in the week.
Okay.
I concur with Thursday. Like it's been nice that way.
Okay.
Yeah, same. I prefer the Thursdays, but that's just what works for me.
Thursday has been good, so.
All right, I guess we'll keep it on Thursday then. So I have a decision to make though, because when I was planning your next homework assignment, I'm worried that well, I'll have to think about how to structure it. All right, so I don't have it done yet, but hopefully by the end of today, there will be a new homework set that will be due a week from tomorrow. And as I said, you can already start if you want, because the first problem will be the second problem on the midterm.
Sounds
Okay.
good. Thank you very much, Dr. Martin.
Thank you.
Thank you.
Thank you so
All
much.
right, everybody,
Thank you.
have a good day.
Thanks.
Doctor?
You too.
Professor,
Yes.
I've been wanting to ask you